have the screen already, I think.
Okay. That should do.
Okay. So this morning I will talk about AllegroGraph 2.0, a thing that we call a Web 3.0 database. We just released AllegroGraph 2.0, so you'll be the first people outside of France that will see how this new graph database for RDF triple store works. AllegroGraph, I will have a few assumptions in this seminar. One of them is that you already read a little bit about the semantic web, and you are a little bit familiar with RDF. Not too much, I will go over the basics of RDF, but still I assume that I don't have to go really in depth there. The other thing is that AllegroGraph 2.0 is a product that is mostly used by people that program in Java, but in order to give my demo, I need some environment that is more interactive. So all the demos that I will do this morning will be in Lisp and in Emacs. I hope you guys can live with that. I will give a little Java snippet so that you can see that there's not much difference between what we do in Lisp and in Java. Okay, is there anything else that I have to start with? Okay, so let's jump in it. My marketing colleagues at Franz want me to call this AllegroGraph database a Web 3.0 database, and I hate hype words, and I resisted in the beginning. And then they showed me this picture by Nova Spivak, and my screen is frozen. How do I get to the next screen? It's down. Okay, so this is a picture that he recently published where he shows some progress or some trends on the web and in computing technology. And if you look what we do with AllegroGraph, you see that we're basically in this area. We do RDF and OWL and Sparkle. We do semantic search. We can do distributed search. All this business is about that this is a semantic database. And then part of my talk this morning will also be about how people use this as a social networking tool, especially as a social network analysis tool. So in a way, my marketing colleagues are right in that I could call this thing a Web 3.0 database. But that's all I'm going to say about the general semantic thing. Most of the rest of what I'll talk about will be very detailed and technical. First, I will explain a little bit about what RDF is, and that RDF is nothing more than a way to serialize old-fashioned semantic networks. I will show you the basics of AllegroGraph, and then within AllegroGraph we have two retrieval mechanisms. One is Prolog, and the other is the standard Sparkle, and I will give detailed demos of both of them. Then our triple store has a few features that are new or special with respect to the other triple stores out there. One of them is that we can do very efficient range queries over numeric values. The other thing is that we now offer a complete named graph support, which is also supported by the Prolog and the Sparkle. And for people who don't want to program in Lisp or in Java, you also can set up this triple store as a server and access it through an HTTP interface. The triple store is basically designed to be a triple store that is focused on storing triples and retrieving triples as efficiently as possible, and we leave it up to other people to provide graphical user interfaces or full description logics. However, we've talked to many customers. The previous version of AllegroGraph has been tested by several people who wanted a simpler form of reasoning that was predictably fast. So we created our own reasoner, and we called it the AGraph RDF++ reasoner. And I'll just talk a little bit about that. I'll show you a product that's provided by one of our partners called Top Quadrant. They have a beautiful tool called Subrate Composer that you can use as a graphical interface to AllegroGraph. And finally, if I have some time left, I'll talk a little bit about how you can use AllegroGraph for social network analysis. Any questions so far of things you would like to focus on so far?
One question listed as kind of a functional programming. Just maybe just kind of a statement about list for the non-list people.
Okay. I'll talk about this when I do the demos, and I'll go a little bit more in detail when I try the list part, when I do the demos.
Okay.
I'll explain a little bit about that. Okay, let's first focus on RDF. So RDF stands for Resource Description Framework. It is a W3C knowledge representation standard for the semantic web. The whole dream behind this concept is that in a few years' time, every snippet of information on the web, whether it's an HTML page or a picture or a movie or whatever, has some metadata attached to it, so that it becomes easier for agents and machines to find information that you need as a user, to find it back more easily. It probably will take a little bit of time before that dream is realized, although if you look at things like Flickr and YouTube and many other services, you see that metadata already is becoming very, very important. But independently of what you see on the web, another thing we see is that RDF is just, very quickly became a standard for metadata in general. And then for people that had a little bit of AI in their education, when they look at the RDF stuff, they will, after a while, figure out that, hey, this RDF stuff might look complicated, especially the whole XML part of it, but actually it's nothing more than a way to serialize old-fashioned semantic networks. Now, what do I mean by an old-fashioned semantic network? This is probably the smallest ontology in the world, of the animal kingdom. So you have a thing, class mammal, which is a subclass of animal, which is of type class, and a mammal might have 2 eyes, 4 legs, and a dog might be a subclass of a mammal. And then within an ontology or in these networks, you also specify predicates, and predicates in semantic networks are objects too. So predicates have their own properties of predicates. And then below the line, you see some individuals that are actually described by this particular ontology. So, for example, there's a node called Jans, and there's a node called Mr. Aasman, which is actually the same as Jans, and there's a thing that is a pet of Jans. I'll get back to this example later, but this is a semantic network, and computers, of course, need to serialize these things before they can reason over them. So, what you need to do when you want to do something with these networks is you create triples. So what you see here, this particular picture, is completely serialized by these triples here. So each triple has a subject, a predicate, and an object. Mostly in the semantic networks of the separates, we call this thing an object attribute value, but so this confused me enormously when I started this stuff, but just remember subject, predicate, object. Now, one problem with these short names was that people got confused. There's a big chance of confusion when multiple people create ontologies, because the same person or the same person might call a concept with a different name, or multiple people might call different things with the same name. So one thing that the RDF people did is say, okay, hey, all these nodes need to be unique, so let's add a namespace to it. So here you see again the same semantic network that you saw before, but now with namespaces. So when there is a namespace, we call one of these nodes a resource. So here you see the animal. And if there's no namespace, then you call it a literal. And for people who have a tendency to masochism, they even invented this RDF XML notation. And this is a little example that I'll give you a demo about later. It's an RDF file about terrorist networks. Okay, so I showed you that the triples. Now, people that built triple stores initially started out by working with these long strings, but it is incredibly inefficient. You have to do lots of string comparisons. So basically every triple store now does the following. All the strings are replaced by numbers, and the strings go into dictionaries or reverse dictionaries. So again, here we have the same semantic network, except now we see that animal, 4, type, 5, class, and then 6 is the triple ID. Now in our triple store it's slightly more complicated because each number is actually a number that is 12 bytes long, or hash code, but the principle is the same. Triples in memory and on disk are just vectors of numbers, and there are dictionaries that map the numbers to the strings and the strings to the numbers. And then in order to find triples back as quickly as possible, you want to index these triples. And I show here 3 indices because we support named graphs, and for some people there will be a completely new term and won't have any meaning. So actually we work with 6 indices lately. But anyway, so what we do is we index triples. One index thing is subject, predicate, object. So if you want to get a triple out of the triple store, you will specify get triples and say you want to triple all the triples that start with Jans. Then you will do this call, and you can use this index to get this with one disk lookup if it's not in the disk cache. If you want to find Jans Isse, then again you can jump with one in the B tree. You can jump quickly and directly to the page where you'll find the triple that starts with Jans Isse. And the same for this one, and you probably get it. So if predicate object subject 1, for if the subject is known, and there's even an OSP. I guess that most people will get this particular thing. Now, there's a really big difference between a triple store or a triple database and a relational database. And every time when I give a presentation, people ask me, okay, can you tell me what the difference is in the, as concisely as possible? And basically I've come up with 2 slides that I hope will demonstrate what the differences are. Here you see a part of, or a set of triples that describes someone from the Kennedy family. I will use the Kennedy family in my demos all the time. I will basically do all the Sparkle and Prolog demos using a little database about the Kennedy family. So this is a little chunk out of this file, or out of this database, and here you see that there's a person with the first name Rose, a middle initial Elizabeth, last name Fitzgerald. She went to this school. She was 105 years old when she died. She was female. She had lots of kids, and she had and her profession was a homemaker. Now, what you don't see in here, but one of the points I want to make is people could have gone to multiple schools. People could have multiple spouses. Well, people have multiple children. People could have multiple professions. So in a triple store, you don't have the indirection of relational databases, but you can just directly represent all the one-to-many relationships, or many-to-many relationships. And so if I take the same information here, if I want to put the same thing in a relational database, I will get this picture. So this is again the triple store that I will show you later in my demos. And if I would have to put the same triple store in a relational database, this would be roughly the schema that I use. So I would have a table person, where every person would have an ID, a first name, a last name, and a middle initial. a date of birth, a date of death, a place of birth, and a sex. And then people can have multiple spouses, so I need an indirect table to tell that person 1 was married to person 2. People might go to multiple schools, so there's a table to link people to schools. People have multiple professions, so I have a table to link people to professions. People have multiple children, so you can use this table. And then people all live in the town, and so people point directly to the towns they live in, or the town they were born in. And this town again has an ID, a name, a state, and a longitude and a latitude. And so I hope you guys understand why there's such a, what the real big difference is between a relational database and a tuple store. And summarizing, what you can do with a graph database is you can add new predicates without changing any schema. So if you are the maintainer of a really big relational database in an enterprise, then you probably would get completely crazy if 10 times a day someone came to modify your schema. It would be impossible. But graph databases are just built to add new predicates all the time. The other thing that I pointed out is that one-to-many relations are directly encoded without the interaction of tables. So many queries can be expressed much simpler, and much queries are done a lot faster just because of this. And then finally, in a tuple store, everything is indexed. In a relational database, you spend a lot of time thinking, okay, what are the things I need to index? In a tuple store, everything is indexed for you, so you don't have to think about it. There's a price, of course, on this, but at least you don't have to think about it. And it will be always fast. So we have this tuple store. Before I dive in the demo just a little bit more, what we cover with AllegroGraph is everything in the standards for RDF, so based on Unicode and URIs, XML and namespaces, RDF and RDF schema, and then we do ontologies, and we even have a simple form of logic. If you really want full description logic, you can buy Razor Pro from us, and that does all the way from OWL, full description logic, to Swirl, and things like that. This is the stack of our product. We run basically on every platform because we have a compiler that runs on every platform. Then on top of that, we have this graph database with dictionaries, indices, and caches. On top of that, a really simple API to store triples, to get triples, or to read a particular file. Then on top of that, we have a reasoner that you can turn on or switch off. The one that I'll demo today is AllegroGraph, RDFS++. And then on top of that, we have our query engines, Sparkle and RDF Forward on Lisp. And for people who never want to see Lisp, there's a big black box, and you can talk to it over HTTP with the REST protocol, or you can access it in Java. Okay, so now let's jump into the demo. But before I continue, anyone with a really pressing question, please push your 6 and let me know. Okay, nothing on the chat.
Hello?
Yeah?
Hello?
Yes?
Okay, I had a question about your analogy or comparison with databases. It implies that you can't control the addition of triples in your triple store by having defined a schema which you have, which the triples have to conform to. Is that true or false?
I don't completely understand the question, but with the triple store, you can, on the fly, add any new predicate that you want, and basically you then have a new schema. But maybe you can summarize your question again.
Well, let's suppose you had a schema or an ontology that defined the structure of the structure of the graphs you wanted to store in AllegroGraph.
Yes.
And then you would, you might, in analogy with the relational database, you might not be able to add triples that didn't conform to that schema, say if they were the wrong data type, or if cardinality had been
oh, sorry, yes, you're right.
violated.
So,
Okay.
AllegroGraph is a thing that will eat any triple that you throw at it. Yeah. So if you have an ontology, say for a person, and you want to make sure that that all the triples that you add about a person fit into the ontology, you have two choices. Or you add a new predicate to the ontology, so then the new triple would be valid, or the triple would be just in the database, and it is up to you whether you want to work with that or not. Or what some people do is they write a program that before they add a triple to the triple store, they first check in the ontology whether or not the triple is allowed to go in. However, that is up to the application programmer. Currently, we don't have a mechanism to enforce that new triples adhere to a particular ontology. The whole point is that usually what you see with people that work with ontologies in triple store is that they modify the ontology all the time. Yeah, so many times they might write a new ontology to fit the data instead of having the data fit the ontology. But there's no inherent mechanism in a graph that will listen to the ontology to see what or what not you can add. Is that clear? Does it answer your question? Okay, thanks.
It does.
Okay, let's go to the demo. So this is good old Emacs, and you're looking here at Lisp. Just very quickly, Lisp. This is just like a scripting language. I can type numbers and they get evaluated. I could type a string, gets evaluated. I could write a function called dfun add a and b. I could do it a and b, and I could say add and this, and the numbers would be added. Now this is a interpreted version, so I can compile. Oops, I hit the wrong button. Now it's a compiled function that will work a lot faster, and to prove that Lisp is no longer an interpreted language but just a compiled language, we usually do this for a second. Okay, so this is the listener. I'll open a file that contains the script of all the things that I want to demo today. For people that are interested, I can send you this script later so you can study all the things that happened today. If I go too quickly, you can look at it later. If someone reminds me here, I also save all the outputs, so I could even add that so you could see what I did. So what I also do, which might be good to realize, is I will be so on the left-hand side you see the editor, on the right-hand side you see the listener. What I'll be doing, What I'll be doing is I will type a key that will copy the expression on the left-hand side, put it on the right-hand side, evaluate it, and then the cursor jumps back. So right now, I clicked on load triple store, it was copied to the right, it's evaluated. So now I have loaded the triple store. I need to be in a particular namespace or package, just like the Java namespaces, so I'm here. And then for the demo, I create my first triple store. So I create a triple store, I call it seminar. It goes in a particular directory, and if it exists, I will supersede it. Okay, so I create it. So now I have a triple store, and because I'm lazy, I don't want to type all these long URLs or URIs. I create a thing. I create a mapping between a short string and a long string. So I'll be using the namespace O all the time, but O will actually stand for the HTTP www.franz.com simple. So I'm doing that. So what does it mean? What can I do? For look at the left-hand side. So if I do bang O person 1, then what actually happens is that I get this thing here. Yeah, saves me an enormous amount of typing, and I have a fighting chance to keep the content of my strings on screen. So now let's do the most simple thing. Let's add a triple to the triple store. Yeah. So let's add the triple that there's a person 1 with the first name Steve, and that Steve is an organizer. Yeah, so I add a triple Steve. I add a triple that he's an organizer. Then I add something about myself, and that I'm a psychologist. And now I want to see all the triples in my triple store. So here you see in n-triple notation all the triples currently in the triple store. And because I don't want to type this stuff all the time, I wrote a little function called show triples that does the same thing. But I use what I call the concise format, so now I can keep the information on the screen. But internally, it's actually this stuff here. Yeah. So now, in my PowerPoint, I showed you that we have these indices to find information quickly back. So here I say, okay, find every triple where the object, so the last part of the triple, is psychologist. I'll do that. And I find that person 2 is a psychologist. And I'll talk later about this thing here, so don't worry about it. I'll get to that later. And I can say, okay, find every triple where the predicate is first name and the object is Steve. And I find that person 1, well, this is the triple for person 1. Yeah. Now I can get triples back. Now internally, I told you that these triples consist of very long, unreadable numbers. So if I do say get triples, give me all the triples, I could type get triples list. I get something really unreadable, but listeners might see that this is a list of factors. So let's take the first one of that. So set a triple to the first of the last expression. So now we have one triple, and this triple is just one long list of numbers. Can't do anything with it. However, all the information that you need is really in this vector. So I could say, okay, find the subject of this triple, of the triple. Again, it's kind of unreadable because it's 12 numbers. So if you really want to see what it is, you type subject. And then you see that this is person 1. Yeah, I hope this, and I can do this for the object and I can do this for the predicate. I showed you how I can add triples. I showed you how I can show triples and how I can do that selectively. And how you get to a part of the triple, and of course I can delete triples. Yes, so I can say, okay, delete every triple where the subject is person 2. So I will delete them. And if I now say show me all the triples, I get only Steve, the triples about Steve back, and that's it. And then I can close the triple store. And now so this is the very, very basics of how you work with triples. Is there anyone that has a question? Am I going?
Yeah, one question. Can you run methods when you add or delete triples?
What kind of methods? Oh, triggers.
Well, similar to what would be like if added or if removed methods to perform some sort of computation or store records or whatever you wanted to do some sort of inference when new triples are added or else when a particular triple is removed. Or
yes.
a particular kind of triple.
So triples are sorry, I hear echo.
We'll turn off our phone, sorry.
So on the roadmap, we definitely have triggers. That's one answer. So for the next quarter, we will have triggers that you can program as a programmer. So you just specify if a particular predicate of this type comes in, then do this with. Slightly more complex is that it's the truth maintenance issue, but okay, no, let's not talk about it now. So for next quarter we will have triggers. Let's keep it at that for now.
I have a question.
Yeah?
This is Marco over Lanel. My question is, with the whole interface, the thing I like to take away from this the most is how do you get that up arrow to key to work like you do in Bash? Because when I'm coding in AllegroGraph, I have to always cut and paste from a text file, and I just want that up arrow to work.
So what's the work there?
You know what I mean? So when you're in your terminal right here, and you push the up arrow, you get a funky little character. You don't get the last command that you just executed. So when I'm coding for AllegroGraph, I'm always writing in a text pad, and then copy pasting my instructions in.
Oh, Emacs versus VI? Sorry.
I don't know. I just run it from the terminal and run mlist 8.
Yeah, but
and then right there it drops me into the AllegroGraph terminal, just what I see right here on the screen.
So what I'm doing,
I don't like to copy things over. I just want to have the up arrow give me the last command, like in Bash. When you push up arrow, it gives you the last command that you just executed.
oh, I can. Well, yeah, I can do it in the listener. I can type this. Oh, I closed the triple store. I can't do that anymore. In Emacs, I can type : and the last command that I did was executed. I can also. Huh? Oh yeah, in the listener. Sorry, only in the listener you can do that. Hey, write me an email about that. I think that's a user interface question here.
Yeah.
We can help you with that.
Cool. Thanks.
Okay, so now just to make sure for people who are who want to do this thing in Java, I have this simple. This is almost the same demo I just gave you for the basics, but now in Java. So this is a 2-page program where you connect. So here you connect to a server. So what you have to do is you first start up a server, and then you just try to enable the tuple store. Then once you have the connection to the server, you specify the name of the tuple store and the directory where the tuple store should go. And this one opens the tuple store. Then you can add tuples one by one by add statements. So here's a very simple tuples: sub1 predicate 1 object 1 sub1 pred 2 object 2. And if you want to send, so every time you do it, you send one tuple over a socket. That might be very inefficient, so you also can send a bunch of tuples over the line. So with this statement you can do a whole bunch, and if the subjects already know, you don't have to specify it. So this is also a very efficient way to specify tuples in Java. And this is the get statement that I showed you earlier. So you specify wildcard. It's a null, yeah. So basically, this returns all the tuples in the tuple store and then prints it out. And then you close the tuple store. So this is, if you want to do this in Java, we have a whole series of little example programs that mostly what I show you today in the Lisp code is also done as a little Java example. So don't feel left out. Okay, so now let's do something more interesting. Let's read in an ntuple file. So it's an ntuple file with the Kennedy family. So here you see that there's a person1 of RDFS type. Person who's got a first name Joseph, a middle initial Patrick, a last name Kennedy, no suffix, went to Harvard. Also was quite old when he died. And then a bunch of kids. Yeah, so this is, and then down in the file I also have all the places where people lived. So here are all the places: Brooklyn, New York, Flushing. Now, by the way, most of the information in the Kennedy database is very accurate. Yeah, those are really the children, really the birthdays, except we couldn't find the places where people were born. So for the Americans in the audience, this is completely false information about the places. I hope you don't mind. Yeah, so this is the triple store about the Kennedy family. So let's go to the Lisp again. I can do this here. So this is the pattern for how you usually work when you create a triple store. First thing what you say is, okay, let's create this triple store. We saw that before. Then we say load n tuple file. We also have a function called load IDF XML if the file is an IDF XML file. And then we index all triples. We have to do index all triples because usually the system, so if you add a triple to AllegroGraph, it will be instantly available for processing. However, we index in batches, so and we have a particular variable that determines when you do the indexing and the merging with all the B trees. If you want to have indexing immediately, you call index all triples. So I run, not compile this function, then I run the function. So now it's done. Oops. And now let's show all the male people in this little database. Yeah? Show all the triples where the object is a male. And I get these people here. So now we've established that there is a triple database. We can look at the triples. So let's now go for a little bit back to the PowerPoint presentation. One way to get information out of the triple store is the prologue. As a matter of fact, I just read a wonderful blog about RDF where someone said, I never really understood how RDF worked until I read a prologue book, and then I instantly got why or what you can do with RDF. But that is a side note. Anyway, we have a prologue that is embedded in ACL. It's completely compiled down to machine code, so it's very, very efficient. And it conforms to the ISO standard and the Claxon and Mellish prologue. And it's compatible with the commercial prologues. And what I'm going to show you in the demo is what this you saw before. I showed you this before. And then I'm waiting for my next page. I'll lead you through a number of predicates, so I don't have to do that in the PowerPoint right now. Let's go back to the demo. So what you see here, I'm going to talk about this part. Basically, this says, find every X that has the sex male. There's a little bit of an echo, Steve. Okay. This means this little thing question mark dash means do an interactive query, and then the Q is the link to the triple store. And basically Q is something that calls get triples, where you specify the subject, predicate, and object. So let's just do it for a second. And what you see here is the first X is this particular guy. Oops. Now these are these horrible numbers, so let's just stop it. I can do it a little bit better. I can say, find every person X where the sex is male, and then in Lisp print the string representation of this particular X. So I can do this again. Now I've seen that the first person is person 31. And the next person is 58, and the next person is 73, etc., etc. But again, that is relatively ugly, so I define a little function to get to the full name, and just don't even try to understand it right now. Basically, I concatenate a first, middle, initial, and last name of the person. But I write a prologue function where I say X has a full name if in the tuple store X has the first name Fn, and in the tuple store X also has in the middle initial Mn, and X has a last name Ln, and then in Lisp bind full name to the concatenation of these things. This is a little bit hard prologue. I'll get back to a simpler prologue later on, but I want you to see what we're doing here. So I take this guy, F8, and now I have, so by the way, this thing means add a prologue rule, this thing, and wipe out everything else you knew about this predicate. If there's only one dash, mean add to the definition of full name. So now we have a prologue predicate called full name in the system, and I can do something like find every full name where X has a full name, and then I will see that this person X has this full name, and I can run again through all the people in my database. I won't do it now because I'll get to that later. I will also jump over this particular function, and now let's get to the simple part of prologue. So we have the tuple store, and in the tuple store you saw some basic information about the gender and whether people are children or not. So what I'm now going to demonstrate is that I can build an entire layer of rules and several layers of rules on top of prologue. So let's start with the simple stuff. Yeah. So I now add to the prologue that X is a male if in the tuple store X has the sex male. So now I have a rule. I can test that. I can say well, Mark Kennedy Shriver is a male, Christopher George Kennedy is a male, and Michael Neil Allen is a male, etc., etc. Or, but this is interactive. We also have a non-interactive version, which is select, which looks a little bit more like Sparkle, where I say, okay, select every first name where X is male and where the full name of X is full name. Yes, so I use this function that I defined earlier to find the full name. And basically with select you say only print the first name variable and don't bother with the X. So I do this, and now I get this whole list of people that are male. Do list for every element in the last expression. Yes, so here are all the males in this little database. And because the return of a select is a list, I could even do stuff where I say, okay, sort the output of the select, base it on string smaller than, and use the first element of the list. And I would do the same thing, and I would get all the people back, this time sorted. Okay, so that is the select. So now the rest of the rules, once I already defined the male, female is of course roughly the same. Then on top of that, I can specify a father, where I say X is the father of Y if X is a male and X is a child Y. And X is the mother of Y if X is female and X is a child Y. And just for fun, let's do this. Select X. Well, let's do this. Prologue. Sorry. Q. O. Person 1. Father person 1. X. Yeah, so well, you probably get that. Then on top of that, once I've defined the father and the mother, I can define parents. So I can say, well, someone is the parent if you're the father of someone, or the parent of if you are the mother of someone. Note that I now use only one dash here. Then once I've done the parent relationships, it's easy to define a grandparent, because a grandparent, X is the grandparent of Y, if X is the parent of a person Z, and this person Z is the parent of Y. Yeah? And then grandchild is just the reverse. And then I get to the part where we have our first recursive query, because I can say, well, X is the ancestor of Y if X is the parent of Y, or X is the ancestor of Y if the X is the parent of a person Z, where this person Z is the ancestor of Y. Now, this is one of the things that I always find easy to explain why a graph database is, or a triple store is different from a relational database. This will be a lot tougher to do in SQL. You can do it with SQL, with Oracle, but it's a lot of code. And if you get really deep connections, you kind of get stuck in cell joins. But it's doable, but it's very, very elegant to express and very fast to do in a Prolog. And this is also different with Sparkle. Sparkle you roughly only do on what I call the naked triples. But here, this whole ancestor thing is built on layers and layers of rules. I hope people understand it, and I'll just stop with the Prolog because I can. A descendant is just the reverse. The aunt is like a little puzzle. And if you get this list, if you get this seminar.cl thing from me, you can look at it and try to figure it out for yourself, how this works. And then nephews. Anyway, so I'm probably now 8 layers deep. Yeah? So I've here. Yeah, let's skip this part. So any questions about the Prolog so far?
A few general questions.
Okay, please.
First question, can a triple store be used in a client-server configuration?
Yes. So the general question is, it's got nothing to do with Prolog, but I can take this question now anyway. Yes, AllegroGraph 2.0 is a server model where you can have multiple clients, Java clients, connect to the same triple store, and we have a Sesame 2.0 HTTP interface completely implemented, so you can have multiple people accessing the triple store over an HTTP protocol, where each HTTP interaction is a full transaction. Right now, for the AllegroGraph 2.0 for this quarter, all the queries and additions of triples are serialized on the backend. For the next quarter, we'll have more sophisticated transactions. Does that answer the question of the person that asked the question?
There's another question. Can't we make AllegroGraph functions generic functions so that users can easily specialize those functions?
The question is, can you write generic functions over AllegroGraph functions? One thing that we want to do is, right now, triples and these hash codes that you see are just vectors, but we're thinking of making the triples a native Lisp data type that just fits into our type hierarchy, and then basically you could write methods that specialize on triples.
Okay,
but I don't know if that answers the question.
There's one more. Is indexing linear in time with the number of triples in the database?
Okay, the question is indexing linear with the number of triples that you add to the database. Okay, the model that we have, if you insert triples in the triple store, you get constant time. Because what happens is that on multiprocessor machines, all the indexing is done in the background. So we use a clustering approach where new triples are added to the transaction log, and after a certain amount of triples, these triples will be added to B trees, and B trees will be merged with the available bigger B trees. It's an interesting topic that we describe extensively in our documentation, but it is n log n, the indexing, but because we do it on multiple processors, But if you're done with loading, usually you're almost also done with the indexing.
Okay, I've got another question about Prolog. Since you've demonstrated interactive Prolog, can Prolog be loaded and compiled as a back-end reasoner over a triple store?
Yes, if you enter a Prolog function, sorry, the question is, can you load and compile Prolog and use it to reason over a triple store? Yes, what you can do, even if you are a Java programmer, is you can write your rules in a separate text file. You load the Java code, you load the Prolog code into the Lisp. Every Prolog rule is automatically compiled anyway, and then you can do Prolog queries, both in Lisp but also from Java. And we have a Java tutorial that demonstrates how to do Prolog from Java. More questions, or can I continue?
Multiple Lisp clients?
Can we do multiple Lisp clients? At the moment, we focused more on the Java part than on the Lisp part. So we can have multiple. We have a full Sesame 2 and some part of the Jena libraries to access triple stores. But if you are a Lisp, if you want to have multiple Lisp clients, you would have to use the HTTP protocol. We're thinking about also adding a direct socket connection and a lower level interface for Lisp clients. We haven't implemented that yet. Except, of course, if you want to work with the HTTP version, and you can do that. Okay, let's go to Sparkle. I'm being told that I have to speak up a little bit louder. I hope I'm not yelling in your ears right now. Let's go to my PowerPoint again. So, roughly a year ago, when you tried to go on the web and find information about query languages for triple stores and for RDF, you would have things like Circle, and you would have many, many different languages. Right now, it's pretty clear that Sparkle is by far now the most prominent language to query triple stores. If you want more information about Sparkle, just go to the W3C website, and there's really good tutorials and explanations of how Sparkle works. If you look at Sparkle, and I'll demo it to you, but it looks like a mix between Prolog and SQL. The advantage of Sparkle over Prolog is that there are some constraints on what you can do in a Sparkle class. For example, you can't call a recursive function. So you can write query optimizers that look at bindings, look at how big particular predicates are, and so you can write query optimizers that are much harder to write in Prolog, because in Prolog every predicate might be a recursive thing, looking at other predicates. So you as a human being have to do the query optimizing for Prolog, and I'll give you a little demo of that later on. So in some cases Sparkle will run faster than Prolog, but then again Prolog is far, well, in some cases more expressive than Sparkle, and it all depends on your application, what you need. For the next quarter, we also will allow Sparkle to run on top of Prolog rules. So you can specify Prolog rules and access these Prolog rules as if they were triples in the triple store. But let's not talk about it too much now. Okay, here's a little example of Sparkle, but as I'm going to demo Sparkle in my demo, I won't even do it here in PowerPoint. Let me go back to the demo. Yeah. So we are still in we still have the Kennedy database open. So now I want to use Sparkle too, so I say use the package Sparkle. And the first thing I do is I run Sparkle from Lisp here, but later on I will also run it from a web page, and in our demo examples we also have Java tutorials where you can see how to run Sparkle from Java. So this is a simple query that everyone can read. You first specify all the prefixes so that you can actually read the classes. So there's a prefix O, which stands for this thing, just like the register namespace. And then you say select every X where X has the sex male and where X has the alma mater Harvard. So this thing means that there will be multiple classes about X. And so I can run the Sparkle. And what I get back is that there is a person 47 that went to Harvard, and there's a person 3, and a person 17, and a person 1, and a person 4 all. So what it gives you back is XML. Yeah, but that's just one option. If you just want to count how many there are in Lisp, and also from a web interface, you can say, okay, how many results do I have? So then you have a little. So you can specify multiple research formats. I think we have roughly 15 result formats. So you can return things like as an array, or as a list, or as an association list, or well, let me just run that. So there were 5 results for this query here. And then, and if you are a JavaScript programmer, and say you want to build some, I've never done this personally, I just know that JSON is a format that is used by JavaScript programmers. And so a JavaScript programmer could send a query to a triple store and get the results back in JSON, and people have told me that that is an easy format for JavaScript to parse. So let me do this. And then you get here something that, again, I've never tried this myself, but this is the JSON format. Okay. For list programmers, you can do a list, but this is very low level, so let's just quickly forget about that. This is a query that goes a little bit deeper, so not important right now. Oh yeah, here you've asked for the profession, so here you have multiple X's, sorry, you get multiple results, so you get now the pairs for X and P back. So you find every person X that is a male, went to Harvard, and has a profession P. And here then see the professions. One was a Navy, one was a president. One was a senator, congressman, ambassador, a banker. Anyway, you get the point. So these Kennedy guys are really doing well. You might have heard from my accent I'm Dutch, so I'm not familiar with the Kennedy example. But so filters. Another thing is Sparkle. Is this thing here. If you want to filter your results based on a regex or on a number or whatever, you can specify it all here. So in this case, I say, okay, find every person, every male person that went to Harvard that has a profession P, where part of P is the word at, and I already know that will be all the attorneys. Yes, so let's run it. And then we find that person 47 is actually an attorney. Then another thing you can do in Sparkle is optional things. So if you wanted to, you can find every person X that is sex male, went to Harvard, had his profession P, and if if this guy had children, then you give these children back too. It gives too many results. Then something you might recognize from SQL, there's a thing called order by, so you can say, okay, again the same query here, and say and order everything by profession. So do this, and now you will see here, and actually I'll do this example I think later on. Well, yeah, these things are now alphabetically sorted on the string profession. And if you only want to see a little bit of, not all, if you don't want to see all the results, but just two, just to get an idea of how the results look like, you can do this thing here. You can do it's exactly the same expression as the previous one, except you now limit it. This is all described in the Sparkle tutorials that we have and on the website of the W3C. So here what you see, you get two results back. Person 1 was an ambassador, person 17 was in the army. And then if you, there's another thing you can do is that you can create new triples by running Sparkle. That's done with the construct. So basically in the construct you say, okay, make new triples of the form X, grandfather, Y, and then you have the query where X and Y are filled, and you return this thing as n triples. Yeah, so I can just run this, and then I get all the people. Anyway, what I got now is a whole bunch of new triples, where someone is the grandfather of someone. I hope this is clear. Yes, this is a way to add new triples. Okay, so maybe you want to see how this works over on a web interface. So let me do some stuff here. So now I started a server which will work on the Kennedy database. So I have to go to this thing here. Let me go to my web page. Let's start a new tab. Oh yeah, this is okay, so this is a simple web interface. And let me just take one query. Let's take this one. I go here. Oops. I put the Sparkle in here. This is completely. Huh? I think this is what I wanted. Let's see what I get. No, this is not what I want. So let me go to the. Sorry. Let's go to this prefix again. No, I don't want to do. I want to do this one. So I do control. Okay, now I go to the web interface. I replace this. How do I delete this stuff? Oh, that's it. Sorry. Yes. I usually don't do this over a terminal emulation. So let me see. No, you can't. You have to do it this way. So, Control, Alt, Enter. Okay, this is it. Haha, so there it is. So now I can. So what I have here is an interface where I can specify in a web page whether I get something back as XML, JSON. Turtle is another way to specify RDF or plain text. So here I can play with it. I say, okay, I want to see only one result. And I do query, and I get only one result back. I can say I want to have something as JSON back, so I do a query, and now I get it back here as JSON. Or I can do Turtle for people who know Turtle, and I get it back as Turtle. Yeah, so this allows you also very simply to play with variations and get a pretty presentation here in any format that you want. Any questions about this? I can close this. Okay. So that then concludes the Sparkle. Let's get back to the right. Let's get back to the PowerPoint. So then there are some new features that we have that are all completely new for triple stores, or we're one of the first to implement them. One is range queries. I don't know yet of any other triple store that has them. And then named graph supports that right now are in a number of other products, and this HTTP interface. So the range queries. We were testing the previous version of AllegroGraph with a number of customers, and people first are enamored with the idea of a graph database, but then when they want to do practical work, they realize they want to do range queries where you say find every person between 20 and 30, or find every event between this time and this time, or find every place between this latitude and this longitude. So what we needed was a much more efficient way to deal with numbers. Now the problem with the triple stores so far was that everything is represented as a string. It doesn't matter whether it's a number or a string, a resource or a literal. So we went to a different scheme, and now these things are native data types for the triple store. And we now can do things like, okay, find every area in a particular time and get it very efficiently back. So I will demonstrate that part. Then the other thing is named graphs. We call this AllegroGraph a triple store, but what we actually are is a quint store. We still have the subject predicate object. Then every tuple has a unique ID, and every tuple has what we call a graph argument, which is just also a resource or literal or a number. People wanted this extra number so that they could cluster numbers of tuples together. You can use it for verification, or what it's very handy for is that, say, you have a tuple store that consists of multiple n-tuple files. So one thing that people do in general is that they then, when they load in tuples from a particular file, they use the file name as the graph argument for the tuple. So that later on, say you modify the n-tuple file that you got from somewhere else, then just with one command you can delete all the tuples that came from the original file and just read in the new file with the new file name. So it's a much easier way to bundle tuples together. And our prologue is now completely integrated with this named graph, so you can specify whether the reasoning has to happen within a particular graph. And when I say graph, I just mean a bundle of tuples. And our Sparkle also works with the graphs. There's a proposed standard for how to work with named graphs, and we implemented that particular standard. Oh, by the way, and what we see is that also many other people that are interested in this technology use the fourth argument not for a file name or anything else, but just for numbers, so that you can specify, say, the distance between two cities. You can say San Francisco distance to New York, and then 3,000. Yeah, so that's and because tuples are completely sorted on subject predicate object graph, you get a very efficient way to find the distance between two places. You don't have to go to 2 or 3 tuples. You just can use one tuple. And what I'll show in the demo is how we use this named graph stuff. Okay, let's go to the demo. So let's close the tuple store. And we create a new tuple store, and this time we specify when we open the triple store, that it's the graph argument will be Kennedy file. Yeah. So we do this. Now we load it. So now it's loaded. And then, so if I do show triples, you get the first 50 triples. And you see that the graph argument is now Kennedy file. And what we can do is now add some more triples where we specify a different graph. So in this case, let's see, this is so we now say there's a person 1000 with the first name Arnold, and the graph is in, say, the namespace interactive. And the last name of this person is De Vries, and the profession of this guy is a professor. Yeah, so we have add 3 new triples to the triple store. And now I can say, for example, okay, give me every person that has as an object the word Arnold. And I will find 2. One is 44441, person 27. It's Arnold, and the other one is the Arnold that I just added. Yeah, so now let's see what are the triples that I added for this particular interactive thing. And I find that it's Arnold De Vries, who is a professor. And I could do the same thing for all the Arnolds from the Kennedy file. So now we see how Prolog uses this. So I say, okay, select every last name and professor where the first name is Arnold, and it comes from the Kennedy file, and the last name is last name, and the profession is profession. So I look at that, and then I find Arnold Schwarzenegger, who was an actor, a governor, and a bodybuilder. Okay. I can also do the same thing for the interactive triples in the name graph interactive, and I get only Mr. De Vries, who was a professor. And the same thing works for Sparkle. So I can, well, this one finds all the ones. So this one, if I do this, F8, I get the professor, bodybuilder, Arnold Schwarzenegger, and oh, I can't get here with my mouse. Anyway. And if I want to say I want to do the Sparkle only over one named graph, then I specify the named graph here. So I say only do your Sparkle on the triples from the Kennedy file. And now I get the bodybuilder, I get the governor, and I get the actor. But that's about it, and I don't get the other one. And of course, this is also the really handy thing. I can delete triples, all the triples that I added in the interactive session. So I do, I delete them, and now they're gone. Okay, any questions about this?
There's one question here. Can the graph object itself be used as a triple? So like to attach additional triples to the graph?
Yes, I will show that slightly later on. One thing we can do with the triple store is that the parts of the triples can be the IDs of triples. So you actually can point to triples, or you can say things about triples, which is a very effective way to do arrayification in AllegroGraph. But I also have to point out that from that point on, when you do that, you live in sin, because you can't. It's outside of the RDF spec. If you do stuff with Sparkle, it's undefined. We're right now trying to see if we can extend the Sparkle protocol to work with this. And our Prolog, by the way, doesn't care. I mean, you can just add it whatever you want to do. But this Prolog, the Sparkle standard doesn't have any provisions for this particular thing, and actually, it's illegal in RDF. But many people find it extremely handy. So,
I think there's one more question along the same line.
Yeah.
RDF uses XML schema data types. So how can everything in a string in triple stores?
I get this. This is. I will talk. Okay, so the question is about XML data types. We currently support roughly 20. How many, Steve? How many? Oh, okay. I can show here. Do list for every element of supported types. These are the types that we currently support. Triple ID, longitude, latitude, telephone numbers, blank notes, literal, short, single floats, double floats, year, time, date, long, short, unsigned longs, and all these things. And what you can do with the triple store, but that leads me to the next part, is the range queries. So let's go there. Close the triple store again. So now we do something else. We can say in the triple store, I open the triple store again, like I did before, but now I say set up the property mapping for birth year to an unsigned long, and set the property mapping for a death year to unsigned long, and take the longitude and set it, well, we have a data type longitude, and the latitude to a latitude. So what I do here is I call this a property mapping. We also have a data type mapping, so that if you have an RDF literal that specified a data type from the XML schema definitions, then we automatically will translate that into the data type representation instead of using it as a string. Okay, so let's just do it. So now. So I close the triple store. Oh, there's no triple store. Okay, no problem. I already closed it. I load the triple store again. And now I could do something like get all the triples in the range. Okay, find all the triples where I don't know what the subject is, where the product is birth year, between 1900 and 1930, and uses the data type unsigned long. So I can do this, and I get a list of triples where, let me see, with all the birth years between 1915 till 1929. And by the way, you also see that they're sorted, because that's how they are in the triple store. They're sorted in the triple store. Okay.
Is there an analysis set of functionality to commit, given there might be multiple clients?
So that's. I'll take this question later, please.
Okay.
Yeah, I'll take this question later. Yes, we have 5 minutes to go, so I'll make it quick. So we can use this stuff in Prolog, the range queries. So I could write a function, but there's many ways to do it. This is just one way where I say, okay, find latitude between x, between minus and max, and then say, okay, translate the value that you have to a latitude, translate the max to a latitude, and then find every x where the latitude is between minus and max. So that's one way to do it. And birth year between, and then I could say, okay, find every person that lives in a latitude between minus 100 and plus 100, where this particular person has a birthplace place where the birth year between for this person is between 1900 and 1930, and the full name of this person is full name. And only print the full names. So I do this. And then I get all the people for this whom this applies. And there's many ways I can do this. I could put it in a function, and let's not even talk about that. Any questions about the range queries? Okay, so the last thing I want to do, 4 minutes left. We have a reasoning engine in AllegroGraph. So see. Yeah. So in RDF, you can say everything you want. You can say that a mammal is of type class, and a dark dog is a subclass of mammal, but a mammal could also be a subclass of dog. RDF will allow it, but in terms of logic, it's of course insane. So in order to allow for systematic reasoning, they added some semantics to RDF. For example, they added the fact that you could say that a thing has a particular type, or that something is a subclass of something, or that a property is a subproperty of another property. Or you have things like domain or range, where you say, well, if y has a pet, if x has a pet y, then x has to be a human being and y has to be an animal. So that's the range part. And then that's very simple semantics. So people added something else, which is owl. It's basically a full logic, a description logic. So now we have something that is a marriage between an object-oriented type system and a well-understood description logic. And you can do all kinds of reasoning, especially class membership, equivalence of classes, see if the ontology that you wrote is consistent, and you can classify instances in your database. And things that we handle, and then there's a lot of new predicates in this OWL language, like same as, inverse of, transitive properties, semantic properties. And what can you do with this? Well, just to give you a simple example, if you remember the semantic network that I showed you earlier, you could do questions like, okay, does Mr. Aasman own an X where X is 2 eyes, given this semantic network? And given that we don't have time, I'll give the answer away immediately. The answer is yes, because Mr. Aasman is the same as Jans, yeah, and Robbie is the pet of Jans, and the property pet of is an inverse of has pet, and has pet has a range mammal, and the mammal has 2 eyes, so yes, there is an X that has 2 eyes. There's an X. Mr. Aasman does have an X that has 2 eyes. We've implemented this type of reasoning in AllegroGraph, and just a very simple example. Just take, if you look at the triple store, show the triples where the predicate is has child. And you see that they are there, but of course they don't have show triples with the predicates child up. Yeah, 0. But now, if you add this triple, where you say that has child has an owl inverse of child up, now suddenly these triples are there. And I activate a reasoner by using this thing called QS. So normally, when I would say, is there a person, does person 7 has a child of X, then I wouldn't get any answer. But if I use this prolog predicate QS means, okay, do prolog, but use the reasoner to get my triples from the triple store. So now if I do it, I suddenly see that person 1 and person 2 are children of. Yeah, so what you see is the prolog works on top of the reasoner. And by adding things like inverse of, I can do the same thing with same as. It's another one that we do. We have roughly 10 predicates that we support, all the RDFS predicates and 4 OWL predicates. So I can say Arnold is the same as the Terminator. Yeah? So now I can say, is there anyone in my database with the first name the Terminator? And yes, person 27 is Arnold. Yeah? Let me see just. I think people have to go now, given it's 11:30. So let's take questions of the people that want to stay around.
I'm going to try something with the phone, because I kind of eliminated people's ability to unmute themselves. Let me try to reverse that.
All callers are unmuted. All callers are muted and may unmute themselves by pressing 6.
Okay, so now if you have any questions, you can unmute by pressing 6.
I have a question.
Yeah.
I I didn't see same class as, same property as in that list of OWL constructs. Is that, do you support that?
What we support is this. Let me see. Let me see. Where are the? We do same as. We do inverse of, and we do transitive property. Next quarter, we will do semantic property and functional property and inverse functional property too. If you want anything more than that, then you have to use something like Racer or Palette. But we have.
What about though? What about same class as, same property as, which is different from same as? Those wouldn't appear to require description logic reasoner.
But is that something from OWL 1.1? Because
No, it's completely standard.
Same class as. Okay, I don't know these.
Okay, you might look up those and
Actually
see.
called equivalent class.
Oh, equivalent class. Yeah. Well, we don't do that. We do same as inverse of and transitive property. That's what most people work with. If you get, and then people ask me for semantic property, functional property, and inverse functional property. If you go to really the complex class descriptions, then you have to use the description logic.
How can you integrate the description logic reasoner with what you're doing? So suppose I have a bunch of complicated OWL, and I have lots and lots of OWL data. How can I, and if I use Racer Pro, how do I kind of use Racer Pro versus use the triple store? How would I even do that? Which part is going to do what reasoning?
It would be best if you write directly to the Racer people and to Ralph Muller. Ralph implemented a bridge to AllegroGraph, so he treats us as an external database that he can read triples from. And what the people from Racer are doing right now is to get to a much closer integration with us. One, by having our Sparkle run on top of Racer queries. Yeah, so you can turn on Racer in the future and then have Sparkle do your queries, but where the triples are returned by Racer. But right now, Racer systems can provide you with a bridge to AllegroGraph. And if you look in Racer Porter, the latest their graphical user interface, you'll actually be able to see how you can actually interact from their graphical user interface with AllegroGraph.
Great. I've got a question too.
Yeah.
Are there standard benchmarks for triple stores anywhere where we could see AllegroGraph compared to other alternative implementations?
Yeah, we somehow time flew by, but what I had wanted to show was a benchmark called the Lehigh University benchmark, which is an ontology describes the organizations, the people, the departments, types of papers in a university, and then there's a generator to generate a arbitrary number of universities, and per university a number of departments, and then there is a set of 14 queries that people write about. And so if you look at those queries, you will see that we are very, very competitive with the speed. For the queries so in the set of 14 queries, there are 2 queries where we get incomplete answers because we don't do full OWL. But if you look at the result times, we are far the fastest. And okay, we run this always on a test set of 50 universities, where each university has 20 departments on average.
What happens if you have so much data that you can't hold it in memory anymore and you have to go out to disk? Do you have a reasonable or does a disk take?
This is a disk-based triple store.
Oh, so it is out on disk.
It is on disk. Yeah, I can close it. I can open it.
Oh, I see. Okay, so it's not in memory then.
No, it's not in memory. Everything happens from disk.
Okay. Okay, thank you. I misunderstood.
Okay. Oh, that's very important. But because one of the things that we advertise with this particular database is that we can do billions of triples.
Right.
And you have to be really rich, like the U.S. government, to keep that all in memory.
Okay, thank you.
Is there a persistent object store for this too?
Well, all the triples are persistent. So if we, for example, we created. So let's look at this is a very quick demo if you're still looking. So let's read in a persistent. So let's read in a terrorist database and a weapons database with 220,000 triples. Yeah. So I'm reading this thing, and we're by far the fastest loader of all the triple stores out there.
Do all the triple stores advertise their speeds?
We do.
I know that you do, but I haven't looked at all the ones out there.
We always try to find them. It's hard.
Yeah.
But again, it's you know about this joke about statistics and lies, etc.
Yes, that's right.
So I always say, okay, try it for yourself. I wouldn't believe me. Yeah. So anyway, I loaded 210,000 triples in roughly 11 seconds. That includes the indexing. And okay, I register a namespace. It's a site database, and then I do queries like this, where it's a really complex Prolog query, and where I find Osama bin Laden influences a particular person Z, where the C has a friend B, this person C has also been in region D, and this person B has been in D, blah 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 blah, all the way to down the belief system Islam. Yeah. But if I look at the disk, then let's say Altix shell CD temp. Did I call it test 11? It's called test 11. So why is it not?
Wrong machine.
Okay. So here you see the disk stuff. So what you see actually is we have 6 indices here. Yeah. So these are the B trees that we have. This is graph, object, subject, predicate. Here, for example, subject, predicate, object, graph, and index. And then it's the metadata. Here's all the string data in there, the dictionary, etc., etc. Just to prove that this is a disk-based system. Does that make sense? Okay. Any other questions?
Oh, yeah, I have one.
Okay.
If I'm talking to an IT manager and I want to convince them that the triple store is something they're interested in, you know, what are the value propositions? So they'll say, oh, I can do all that in relational database. I mean, what's your little story that you say, oh, no, you can't. Here are all the things you do with the triple store. And what are the trade-offs? So obviously, it's not a panacea. There will be some trade-offs. What's your position on that?
Okay. The trade-off is that, okay, with the triple, okay, when I think that even in 50 years there will be relational database around because they're so important for the enterprise. And there's 10,000s of man years in making sure that the joins are done extremely efficient in a relational database. And all the administrative procedures around things like Oracle are highly optimized, and you need that kind of stability for a database. However, if you want to do graph search over your database, yeah, for example, we have telecom data that we store in the database, and we want to do degrees of separation between person A and the person C through a series of other people that you called. And you don't know in advance how many steps there are between person A and person C, then a relational database, although it will have the mechanisms like in Oracle to do a recursive query between 2 points, will really quickly slow down because of the self joins that they employ in this stuff. So it is a graph database is specifically written to make that kind of stuff go fast. Then the other thing, if you look at this particular query, like you're probably very much aware of how SQL works, but can you just close your eyes and imagine how you would write this particular query in SQL? Yeah. So say you're an analyst and you have this particular type of query. It would take you a long time to write this query and a lot of agonizing to put this all in selects and where and whatever statements and joins to get this going. So you can do ad hoc queries in a much simpler way than you could do with a relational database.
Jan?
Yeah.
I'm sorry to interrupt you. This is Johan Bon at Los Alamos. We're heading off. Thank you very much.
Okay. I hope you enjoyed it.
Yes, very much so. Very informative. Thank you.
Okay. Bye-bye.
Bye-bye. Doei.
Doei.
So is there a section of the presentation that you didn't get to cover?
Okay, but there was one person whom I didn't get the name of that had this question about the value proposition of triple stores. Would this work in your IT department?
Sorry, my name is Mike Ushel, who asked that question.
Okay, but would this answer work?
Well, that's a good start. Yeah, those are things that I had thought about myself. I just wanted to see whether that confirmed with your thinking too.
So
what about the database?
Sorry, can I? But I want to say a little bit more about this. If you.
Oh, please do.
Okay, sorry. What did you think of?
What did I think of what?
Well, you said I thought about this, but what was it? What you thought about when you did this?
The ad hoc queries is something that I realized that a triple store would be much better at.
Yeah.
And that there would be some kinds of, that's the ad hoc queries. The degrees of separation, that's actually the same point as the ad hoc queries, is it not? Or is that a different point?
No, that's more like that you, for example, can do a depth-first search or a breadth-first search or a bidirectional search or any social network analysis stuff where you do just the graph queries that you normally would do in memory, which you now can do on disk. And we've built it from scratch just to make that type of analysis more efficient.
Okay.
The
other thing I've thought about is the database schema and the fact that they're really kind of rigid. And if you need to make any changes and all the applications break, are there any differences there that you can say with the triple store? So say you have an RDF schema or an OWL based schema for the triple store. Is that any argument that says compared to a database schema, it's any easier to understand what's going on? Or make changes?
The big difference is that with a relational database, you start with a schema and your data can only go in that schema. With a triple store, you can add your data and you can write your schemas later. And if they don't completely fit, you write some additional rules and then they will fit. So it's just the other way around. Now, of course, you can do it very neatly and start with an RDF and OWL schema and make sure that all your triples fit in that schema. But what I see people do is they actually fit their ontology to the data that they have. So it's the other way around, if you get what I want to say.
It is the other way around. And what's the advantage of doing it one way instead of the other?
Well, if you're in the enterprise, and you have the typical SAP or customer relationship CRM application, you know what your data is like, and you don't need to bother with, you just write your schemas and that's it. But if you are in a new area where you have data sources from different things coming together, from sensors, say from telecom switches, from billing database, you've got many types of databases and maybe even from different companies where schemas differ. So then you get this weird, strange data in, and there might be schemas, but how do you fit them all together? And with a thing like this triple store, it's very easy to say, okay, well, I'll start with the schemas that they have. I add it to the triple store, and now I write some schema code that unifies all this stuff. So, and of course, you can do the unification at the moment you write the triples, or you can do the unification later when you already have the triples in your system.
What about evolution? This is one of the classic problems with database schema. Because the schema are so rigid, because you've thrown away all the semantic information, it's really, really hard to evolve them and even understand what they are. So they tend to get kind of locked in. They're fixed and frozen. Would those issues be different with the triple store? Would it be easier to evolve things because you have a little bit more explicit semantics?
It would be it's absolutely much more flexible. But I don't know if you have ever seen the Spider-Man movies. Huh? With great power comes great responsibility. So you can use it, but you can also misuse it, and you can shoot yourself in the foot. You know what I mean? It's a matter of balance. But the great thing about relational database schemas is that you really have to think hard. But then, of course, once you thought hard about it, it's hard encoded and it's hard to get out. Whereas with the schemas first, it's easy to manage, easy to do, and then easy to shoot yourself in the foot. I mean, if you're in a development cycle and you're early, then the triple store is really, really great. Or if you have to work with data sources, with different schemas, where the schemas evolve all the time, then our approach with the triple store is so much more flexible.
Well, if I can make a comment about that, what about, it sounds like you're writing a lot of either Prolog or lists to manipulate these triples, so a lot of your processing is in code, your data validation, maybe you may have created or imported objects with different data types, and so all those would mean that if you changed any of that in the triples, that you would have to go and possibly make changes in your code. This would have to also, I think, apply to how you process cardinality, so that's usually an issue in databases at least. So you would have to be able to do your processing when there was no triple there, or where there was one or many, or perhaps there was only supposed to be one, but there's several because of duplicated data. So all those would seem like things to me that you would have to write code to handle properly. So what's your comment about that?
You're entirely right. It's a different model from a relational database. In a relational database, you specify a schema, and then you set some constraints on particular. You set constraints, that your data has to live in, both by having the schema or by having explicit procedures that enforce the constraints. And there's a language for that. And as long as your application is happy within those constraints of SQL, then you can use the SQL databases. If it's getting more and more complex, then we have a language that gives you all the flexibility you want. But again, the price is you have to pay some code yourself. So I would agree with what you said.
Could you characterize?
Yeah.
This is Peter Moore. I have a question about a specific kind of query, and I may have missed a description because I had to step out in the middle of the conference. Can you describe how you do numerical operations on graphs? I don't recall how Sparkle supports this. If you wanted to do something, for example, like what are the sales of anything that goes into making a computer in calendar year 2007, and you may have data at various months, you may have data for different kinds of things that go into a computer, and you want to add it all up. Is there a way to do that?
Yeah, again, you have to write code, but did you see when I was talking about range queries? Do you see my screen?
Yes.
Did you see the part did you miss this part when I specified that you can specify mappings for particular predicates. So
I saw that, but I didn't.
So basically what you...
I'm not following.
Okay, so basically when you load triples or add triples, everything you add is a string. Yeah, everything is a string. Except when you specify that it's not a string. Then the elements of the triples will be numeric values. So then you just, if you say, give me the object of this triple, then you get a number back if it was, say, a latitude, a longitude, or a time. And so if you write a little bit of code to add up these numbers, then it's all up to you. But we'll give you the tools.
Your other, I'm sorry, does AllegroGraph support in its queries all the numerical operations that SQL might support?
Well, what I showed, yes. Well, okay, so the problem is if you are in Lisp, which you probably are not, if you're in Lisp, then the tools are just available, because what you get back from a query is a list of values. And in Lisp, I would say, okay, like in SQL, I would say count third element of list. Yeah, and I would get that would be summed up, all the third elements of a list, which could be the purchase order value, for example. If you're in Java, you have to do a little bit more work, because then you get the strings back, and then you have to read the strings, and then you have to add them up, and you have to write specific code. Whereas in Lisp, all that stuff is already inherent in the language. So
I'm pretty new to Sparkle, but I haven't yet learned whether Sparkle supports, select sum of some set of numbers that's returned by a query, for example. I presume that you may need to do that in Lisp with AllegroGraph, not directly in Sparkle.
Yeah, I would have to look it up. Did you see this?
Sparkle does have a lot of operations.
Okay, we'll need to learn more about that. That's just something that we would need to be doing on top of AllegroGraph.
It would really help if you would just send me email. Where's my email? It's my email somewhere. Or you can send it to Steve Sears, the organizer. So whatever questions you have after this meeting, or you didn't have time to ask them, just send us email and we'll reply.
Great. Thank you very much.
Okay.
There are some questions here.
Okay.
Is the source code for the Sparkle webpage and the query exported URL available?
We can make that available. Is the person that asked this question still around?
Ian?
Ian? Ian, are you there?
Yeah, I'm here.
Okay, so your question was if the source code for the web page for the Sparkle query is available. Yes, it is. Can you send us an email?
Okay, wait a minute. I think I'd have the wrong person. I had a different question.
Oh, okay.
Ian Harrison?
Ian Harrison?
Yeah.
Anyway, the source code is available for that web page. And we also have a description of the whole HTTP interface, which is basically HTTP client gets to where you specify a post query or a get, and then you can do whatever you saw in the Lisp demo, but you can do it with HTTP commands. So you can build your own website. You could even do it in JavaScript. Send a query to a server and get back in JSON or XML, parse that, and do whatever you want to do with that.
Can you give us some guidelines on when we should advise people that using a triple store is really not a good choice?
So can you say that again? Harder? Louder?
When it's not a good choice to use a triple store.
When it's not... I would say if you do heavy-duty join operations on very regular data, and you know in advance, and you need the stability of all the administrative utilities that you have, let's say in Oracle, then you would be kind of speculating if you would use any triple store to base your enterprise on that. But if you want to do complex analytics on, for example, your CRM data in your company, then I definitely would use a triple store. Does that make sense?
Yeah, that's good. I'm just, because I like to be honest, I don't like to go around saying, oh, triple stores are everything. I want to say, here's when it's useful, here's when it's not, and be very clear about it, because you want happy customers.
Yeah, I don't see in the first few years an enterprise built around a triple store and have the same functionality as Oracle. That's just not going to work. But if you want to do complex analytics, then we're so much more flexible than with a SQL database.
What is the key functionality that's just not going to happen on a triple store in the short term?
A key functionality that's not going to happen. Huh?
Multiple writers.
No, that will happen.
I'm referring to your last comment, which is the reason for relational databases still being really important. You said triple stores aren't going to have a number of these functionalities. And which ones are they?
Well, the SQL databases right now have implemented things like triggers, constraints on the data that you get in, automatic backup procedures.
You're saying all those kinds, yeah, but those things are relatively straightforward. You've already talked about adding triggers.
We can implement it all very, very easily, but right now that's so in a way, relational databases and things like triple stores are equivalent in the sense that they can store all the data that they want. Yeah. It's a matter of trade-off between flexibility and rigidity. But I just wanted to make the point that if you want to run a big enterprise, then you probably won't do it on a triple store yet.
So I'm saying why? What would stop me from doing that?
If you do lots of yeah.
I was just going to comment, as I understand it, there's no transaction management on AllegroGraph, is there? So.
Yeah, there is. We have transactions. We have, right now it's serialized, so it's, if one person does a very, very large write, a bulk insert in other people's query, then the other people will have to wait. In the next quarter, we implement multiple writes, so then we would have a basic form, a better form of transactionality. One issue with triple stores is that many people do some kind of reasoning on top of their data. And so basically what you do is you use information in all triples to create new triples. So now what happens if you delete triples? Then you suddenly have the problem that your database isn't consistent anymore. Now theoretically, that also is the case for relational databases, because you could write a program that looks at the content of tables and rows and combines it to create new data. But it's a tough theoretical question that happens more in triple stores because people do more reasoning with triple stores. So how did this question start, by the way? I forgot.
Well, I was interested in what specific reasons there are that enterprises are not going to jump over to triple stores in the short term.
Oh, they will for complex analytics and for high-speed loading. I mean, but I mean, also have to remember that if you look at Oracle or DB2 or MySQL, there are tons and tons of supporting enterprise software that all like reporting software. Yeah.
Okay.
That's all geared to relational databases and not to triple stores.
It's just a historical thing. What I'm wondering, that's fine. That's really valid at this time. What I'm wondering is if that's just a matter of somebody getting around to putting all that stuff in, and then we can move to a triple store world, or whether there are fundamental reasons, like you said earlier, RDBs are going to be around for 50 years.
Okay, so
but the argument that there isn't all the supporting software is only valid for a period of time, 2 to 5 years, all that could happen.
Definitely. So okay, one other example would be that we might complain about the fact that the schemas in a relational database are so rigid. Yeah, but it also protects the company from wild changes in your database. And the database administrator is usually responsible for making sure that the company keeps running. And if everyone just could add new schema and make it very flexible, then the whole architecture just
matter
might...
of authority, who do you authorize to make changes?
Yeah. And so, again, so you get ultimate flexibility with the triple store, but I don't know how good it is in an enterprise where you want to have predictable results. You know what I mean? You get more freedom, but you have to be careful with the freedom that you get.
Okay, thank you. By the way, what's your name?
Jans, J-A-N-S, Aasman. Yeah, right.
Have you interfaced this to other data sources so that you could extract data from other data sources and
yeah, we read from relational databases. So we have some functionality. You can take a relational database and read it into a triple store, and we do comma separated files. Now the theoretical difficulty is, and let me show you this, is that it is something that we offer as a service that you could hire us for, because let's see, where's the... You look at this table, yeah, and you look at this one. What you saw here, the triples are just all integrated. It almost looks like one table, yeah, where the predicate differs. If you want to read in this table, say we had the Kennedy family in this database, yeah. Then a naive way would be to say, okay, I take the table person, and I say, okay, person 2 has a first name Rose, person 2 has this, person... But I don't have the children. I could create a table children, where I say, okay, there's an entry called whatever, where the first person is this and the second person is that. But then I have this interaction in my database. What you really want is that this person gets these children here directly. And because lots of semantics is lost in the SQL, you can't look at the stuff. I mean, if someone defined a foreign key, then you might guess. But you really have to know about how this table here basically connects people in this table. And it can get even worse. You could have tables that say, okay, person 2 and 17 has married relationship. The person 12 and 14 have a child relationship. Yeah? Very difficult. So what we do is, when we read in a relational database, is we read in the schema, and then we write some little code that says, okay, this table actually has to go into the person database as this particular type of triple. So that is some manual work that you can't avoid. So that there is, if you just do the dumb approach, you just read in every table, and that's very simple. You just have a function that does that. But it's not the intelligent approach, because the intelligent approach would be that you actually add the children to this person. And for that, you need to know more about the semantics of your SQL database before you can do that automatically. Does that make sense?
Yeah.
What is your email, please?
Here.
Franz.com.
Yeah, you can send an email.
I would, by the way, what works a lot better is, so you always write to ja@franz.com, but for transactional safety, I also would do it to fsears@franz.com. I'm away a lot, and Steve makes sure that I answer all the questions of customers. Yeah, so please, if you have questions, send it to both of us, j@franz.com and Steve Sears@franz.com. Okay, any other questions? Otherwise, I'd like to stop. And if people want to try it out, please write us email.
Thank you.
Yeah, thanks a lot.
It was great. Thank you.
Thanks very much.
Okay.
I'll be sending out a brief survey. Hopefully you can find some time to just give us some feedback. Appreciate your attendance today. Thank you very much.
Thank you. This was great.
Okay. Bye-bye.